Hi everyone. My name is Nicolas and this is Stanislas. So we're from a startup based in Paris called Neuralk. And the idea of this session this morning is to present you tabular foundation models. I don't know if you've ever heard about it before. Maybe with a show of hand, who has ever heard about tabular foundation models or used tabular foundation models? Okay, great. So a lot to tell. So firstly, I will do a short presentation, I hope short, to just explain what are tabular foundation models. What is the difference with trees? I guess all of you have already used gradient boosting methods. And then we will go on to some notebooks just to play around with tabular foundation models, see how it works, and what changed with regards to gradient boosting methods. So tabular machine learning is different from a lot of different tasks, LLMs or images, because we have table data that would show different modalities. We can find text, categoricals, numericals, date times. So you have to find a way to encode all this information when you want to train a model. And there is also usually missing information where you would want to know this information. So we do a lot of pre-processing, and tabular foundation models are trying to change that to be more permissive with regards to pre-processing of the data. And we work with different enterprises, and what we can see is that the range of the size of the tables with which we're going to work is very different. We'll have clients in the medical fields with very little rows, and if you go work in finance, you will find table data sets where the span of numbers of rows goes to millions, which is today still a problem for tabular foundation models. For a lot of time, until tabular foundation models, you wouldn't want to do deep learning on tabular data. Well, it works, but XGBoost was always better. Usually, different papers studied this problem, and they show that the problem comes mostly from the fact that we use MLPs, and they try to smooth all the bias finding data, so they don't do sharp predictions on the different targets, and where tree shines because they can split your hyperspace very cleanly. If you ever try to put tabular data in LLM, well, it doesn't work. Different papers try to fine-tune LLMs on table data, but what's the point if you have to fine-tune an LLM? There's a very large model just to do not much better than a gradient boosting tree. So there is some research in this area, but performance are not there, and it's very expensive, and you have to wait a lot of time before getting prediction. And in 2022, a team of German scientists proposed a new paradigm, TFM. So the idea is to fit a prior fitting network. Theoretically, the idea is that you train a model based on a set of datasets. So samples on which you train these models are datasets, not only rows, but the whole dataset at once. And you want your model to find a distribution in the training set. So you show both training rows and test rows to the model, and you want it to find the distribution of the trained rows and to infer on the test rows. So if you want to make a prediction with tabular foundation models, you push all your data at once in the model. It won't learn on the data. It will just find what happens in the trained context, and then infer on the test. But we will see it more clearly in the hands-on. Okay, that's not interesting. So tabular foundation models have been around for 3 years now. So the first model was TabPF V1. The idea is that it's a big transformer. So you do attentions on the rows and then make predictions to find the targets. It worked fairly great, but was very limited. You could only put a few samples, and otherwise memory would blow up. So the next big advancement was TabPF V2, which did bidirectional attention. So you did both attention on the rows and the columns, features of your data sets, because there's also a lot of information on the correlation between the features. And a few weeks ago, they presented a new model, TabPFN v3, which is the same architectures as an open source model that you could find on the internet. It's called TabICL from INRIA in Paris, where they changed the paradigm, where you do also attentions on the rows and the features, but you compress the dataset before doing the expensive step of attention on all the rows. And we are working on this technology for a year now, and we have also a tabular foundation models that you can use today, which works in the same paradigm like TabICL or TabPFN v3, where you compress the table before doing attentions on the rows. So what's very interesting about tabular foundation models, and what keeps us awake at night when we work and try to find how to improve these models, is that there is three main areas of research. The architectures, easy. But compared to many models, you train this kind of models on synthetic data. So you have to find, it's difficult to find a large corpus of data sets on the internet, clean, that you can use. So we find that the easiest way to train this kind of models is to generate a lot of fake tables using synthetic data. So the idea is to build a graph, put values on the nodes, transformation between the nodes, and then you sample these huge graphs and are able to represent a lot of variety of tabular data. And you generate millions of these kind of data sets, you train your models on them, and then it works. Why? It's still an area of research. So that was the original TabPFN, just attention on the rows. Okay, so maybe more context on the data. We won't use it today. We won't work on the synthetic data, but for practitioners, it's good to know that these kind of models were only trained on synthetic data. So if you're using this model, there is no leakage. We haven't seen your table before, and no PFNs have seen your data before, so there won't be prior knowledge on your data. If you were to try on some open source data, well, it's good, but you haven't seen this data before, even if we've seen a lot of data sets. With regard to the architectures, it's very simple. It's just attentions, bidirectionals, rows, and columns, so it's very expensive. But the latest frontier in tabular foundation models find ways to compress data in order to make inference efficient. And one last area of research, and you will be able to play around with it a bit today, is that you can put your whole data set in the model to do the predictions, but sometimes it's better not to put all the data. The model is going to try to fit on the training samples that you're going to show him. And when I say fit, it's fit a distribution on it. And if it's noisy or not a good representation of the real task you want to solve, it might degrade the performances. So it's an area of research that's quite underexplored nowadays in tabular foundation models. There is some experimentations, but there is no magical recipe to do it. And usually it's come from your knowledge on your data to find the best way to do it. But we've seen data set where removing samples draws drastic improvements on the predictions. And well, it's very interesting and I love it. I don't care. If you want, you can find also, we have a benchmark where you can compare TFMs, because it's not easy to say, okay, interesting technology, but does it work in practice? We have a benchmark where we show the performances of tabular foundation models on a lot of data sets. And while they always outshine gradient boosting methods, I don't care. And what we're going to use today, so in the hands-on session, you can use our API, or you can try using open source models. So either TabPFN, You would just have to use an API key to use their model, to download it from Hugging Face. Or you could use TabICL, which will run locally on your computer by downloading their package. It might be a bit slow. Or you can use our API. We'll give you a voucher to have credits to use it to make it faster. OK, so what we're going to do today, the idea is to experiment with tabular foundation models. So we're going to just fit models on data. We will experiment with gradient boosting, fit, and compare what happens what we do with TFMs. And then we're going to look at how we can clearly compare, try to find is it really better by doing good preprocessing and cross-validation. Yeah, that's going to come back again. TFM are wrapped in scikit-learn framework. There is a fit method, but actually we don't fit on the data. The fit method is just there to pass the data to servers or to stack it with the tests. And the whole data is going to go at once in the model. But the model doesn't learn on the data. Like we don't fit or don't do gradient descent on your data. There is no leakage of your information in the model. And yeah, it doesn't train like an LLM. It's some context. So it's easy to use. You can just replace in your pipeline your classic machine learning methods with these tabular foundation models. It won't change a thing, just the performances, the speed, and problems you can solve. So to be honest, nowadays, tabular foundation models have been a big breakthrough on some particular kind of data sets. And usually it's the small data sets, because being trained on a lot of data means that there is some prior knowledge, and they're faster to understand the data that you put in the models. So they're really good on small to medium tables. You don't have to do hyperparameter search. Like, it's just a model. You don't have to find a number of trees, the depth of the trees on which you want to fit your model. And probabilities that are outputted by these models tend to be very well calibrated. So you don't have to do calibration for the predictions. But the downside is that PFNs are not as good on large tables nowadays. They're still as good as XGBoost, but there is no large gap of improvement on large tables. It's still an area of research, how to scale these methods to very large tables. There is a problem of latency for very, very large tables. It's expensive. You have to use a GPU, because we do transformers, so we do attentions. And if your data is very far from the synthetic data generated, even though the synthetic data generated to train these models have been thought to be very wide, it try to represent all the real data, sometimes you can find a data set which is outside the scope of the training data. Trees, we don't want to replace trees with TFM. It's just a new tool. They're still very, very good. And on many tasks, they still beat PFNs. But I hope it's going to change in the future. So maybe we can move on to the first notebook. OK.
Questions first?
Yeah, maybe you have questions first. Some things haven't been clear.
Huh?
Yeah.
Yeah, I'm still trying to get my head around how this works. Is this like unsupervised learning? Because you're not actually learning anything from your data. Normally, you would be predicting a Y column from the training data, but you don't have that. So
We have, yes, you have. Well, that's why it works easily with scikit-learn. Like you have your training data of your features X and your target Y, and you give this to the model, and it's going to try to understand what happens, how from the X I find the Y, like a tree, but you don't train the model. You don't change anything internally in the model such that it finds the way from X to Y. You just show examples, like an LLM. You say, I have this, and I want this outcome. You prompt some context, and your training data is the context.
No, but and yeah, to be very clear, the information about the target is an embedding information that is added to your context rows. So it's not exactly the same. You don't use the target in a loss, but how it is used, the information is as an embedding that you add to your representation and embedding of the rows. So this is how you pass information to the model, if that was your question.
Okay, thanks.
Yeah, I think my question kind of relates to the last one. So is this an encoder-like transformer model? Because I saw BERT there, or is it decoder-like transformer architecture?
It's encoder-like.
Encoder, okay.
Yeah.
So it's similar to the way we use BERT doing, say, I don't know, sentiment analysis or for doing intent classification. Is it kind of similar to that?
It's the same.
Here we're doing this with tabular data.
Yeah, underneath is the same technology. Yeah. Yeah.
What's the parameter count, and is it visible to random age?
So for the parameter counts, it depends on the models. You are counting in millions of parameters. There are some models with 5 million, others with 50 millions. It can run on your CPU. I know that TabICL open source model from INRIA has some codes to make it easier to run on your laptop. It works for small tables. When you have a large table where it's very expensive, so you will have to wait a lot of times.
Thank you. And how the inference handled? Is it from entry to entry, or does it work in batches?
For a dataset, the whole dataset goes at once. You don't split it. You just put all the datasets. And it's just a forward pass.
Okay, thank you.
Yeah.
Doug, just related to the question before, when you said that this is sort of like BERT encoder model. So is that fine-tuned on BERT? Like, just
No.
to classify or?
No. When we say it's like BERT, it's an encoder transformer. It's a stack of transformers, but it's very different actually. So you have your old data sets, and it's, I don't know, 20, 30 rows. You're going to do attentions between the rows. So you would encode, tokenize each rows, and then do attentions. That's the simple version, the first version, TabPFNv1 from a few years ago. But you can also do attentions on the other direction, between the features. So you want to have also a tokenization of your features. So these models, there are two ways of doing this. You would do attention between the features. You create some embeddings that these embeddings updates the rows embeddings, and then you do attention on the other axis. Nowadays, you usually do attentions on the features, and you have a CLS token, so your first, like BERT. And this first CLS token becomes a representation of the row in itself, and then you do attention on this representation.
Yeah.
Is it clearer?
Yeah.
But I think the difference with the BERT encoding style is that the token representation is way more intricate with the context and the data that you show it because of this bidirectional attention. So that would be the main difference. Every token has a different representation depending on the features, the column it belongs to, and the row it belongs to.
Yeah, so it's impacting contrasted learning, right? But try to say that one sentence is the same or not the same as another one with a tail and blah blah blah. So I wonder whether something similar has been done here, and how do you do that? Say, one row is different from the other.
Yeah, we don't train it like that, so there is no contrastive loss. It's not unsupervised loss. It's cross entropy. So since you generate the tables, your sensitivity data, you have access to the truth on the test set. So you just have to do regress the real target and update the weights.
Yeah, I mean there are some models that use representation loss, like some kind of mass language modeling. But like the main loss is a classification loss if you want to try a classification model, or a regression loss, or a mix of both if you want to train a model that does both. But yeah, so this is the main part, a classic ML loss linked to the task that you're trying to solve.
So one more question. In terms of the tokenizer, it must be able to cater for the fact that your data could be both categorical and continuous. So is there something special about the sort of how the data is tokenized, the tabular data, because it's going to be a mixture of, as I said, both continuous and categorical.
So tokenization for most of the models is just a linear layer. So you learn to project the data. You don't have a dictionary of this is going to be transforming this specific vector. In the current research and open source models, numerical, so continuous features and categorical features are embedded the same. So there is no distinction between the two.
But as we said just before, there is like a retokenization depending on the content of your column. And so obviously the distribution shift between a numerical column and a categorical column makes it so that the categorical columns are embedded very differently at the end. So this is how you kind of...
But the model has to learn it.
Break that symmetry.
Thank you very much.
Other questions?
So to access the codes to run the workshop, you have a QR code here to access the GitHub repo. Otherwise, is there a link? Yeah.
Did you say it was trained on purely synthetic data?
Yeah.
And if so, why not the combination? And therefore, how do you actually form datasets to know to account for in terms of creation?
So the first models were trained purely on synthetic data. There was a model trained, it's a team in Canada, who trained a model on real data, which works fairly great. Why purely synthetic data? Just because it's convenient. You control exactly the size of your data sets. You can control
Characteristics.
yeah, you can control characteristics. I know that some models train firstly on synthetic data, then pursue training on a small subset of curated real data sets. Maybe models will come in the future only train on real data. But there is a lot of work into constructing this corpus of data sets and make it easy to push in a model.
I think they are like two intuitions fighting against each other. So real data is cool because it's real, you have the real distributions, interactions, and it's actually a bit hard to mimic real feature interactions, real feature distributions. But at the same time, yeah, it's very scarce. You don't have a lot of real data. There's a lot of garbage data out there. So with synthetic data, you don't have this problem. And you have a lot of availability and you control. So control availability is the main advantage of synthetic data. You can do a lot of specialized work on a specific industry or a specific domain. And so it's really convenient to have synthetic data. And the only constraint is that you have to make it match real data. And it's actually quite hard. And yeah, it's what we've been fighting for when we work on the prior is match real distributions, real feature interactions and such. Makes things that work well, that are well behaved.
So in these notebooks, you can use our model or you can try using an open source model. It's going to be okay for small tables, but if you want to run it on the larger tables, you will have to wait a lot of times if it's run on your computer. So if you want to use our model, the easiest way is to create an account on this QR code, and you can just enter this voucher to have lots of credits to experiment with. But if you prefer to use open source model, you would just have to change the use TFM in the workshop notebooks to select between TabPFN or TabICL. TabPFN, you will have to go on Hugging Face to recover an API key to download the weights of their models. But if you want to use TabICL, you just have to do pip install TabICL and use it straight away. It might be just a bit slower. So does anyone of you work with table data in their day-to-day jobs? Yeah.
Sorry to bother. I just wanted to know how I can start on Google. You said I can do it on Colab.
Okay. Yeah, you can run on Colab if you have. Did you access the GitHub repo?
GitHub.com/Nicolas.
Yeah, Nicolas. Neural with an AI measures, and you should go. You should arrive on my profile. And if you go into repositories here, and normally if you go down, there you have access to.
Yeah.
I'll try to show. Has there been any thought put into time series transformers specifically? So time aware, categorical, numerical features, all that kind of stuff.
So I think a year ago, when TabICL released one of their early models, they tried to apply directly by some, patch encoding on time series. They tried to apply their foundation models trained on non-time classification model, and it worked really, really well out of the box. So it was really surprising to see that just by patch encoding the time series, it was easy to use tabular foundation models that were not trained on time series at all. But okay, so now the time series model have become better and better and better with the new releases. So it's not competitive anymore. And so we're trying to include in the prior synthetic data that we talked, mechanisms that mimic real-time series to train on those specific patterns. But you can use, in fact, the same architecture at the end if you want.
Yeah, if it's a transformer model, I imagine there is some kind of a signal you can just provide.
Yeah, exactly. You just want to find the signal that exists when you patch encode your time series, but you can do it the same way, yeah.
So the first notebook is only about doing first prediction with TFMs, checking everything is working. So we're going to work on very small data sets where we're trying to predict heart disease. And it's one of these data sets where usually, well, you don't have a lot of data points, so it's hard to make a tree converge properly. You will have to find good hyperparameters. And if you were to use the TFMs, well, you don't have hyperparameters, so it works out of the box. And as we were stating, since they are trained on a lot of synthetic data sets or a lot of data sets, they have some prior knowledge on the problem they're trying to solve, so it makes them be efficient on this kind of small data sets. That's why, but maybe in the future and starting nowadays, there's a lot of scientific papers, usually in medicine, yeah, I don't know the term exactly, that use now PFNs to do predictions because, well, it's easy to use. You don't have, you might not be a data scientist if you work in a hospital, so you don't have all the best practice. You don't know how to fit a tree, and it works even if you have just a few patients. So we have different kind of data in these data sets, but it's mostly categorical and numericals. So we're going to do something very simple. This one, we just plain train state split, and then we will see later that you have to do cross-validation to really see that maybe there is a difference between those models. Here we're mostly going to be into the noise of the predictions. Well, it will depend on the fold and the seeds that you put it in order to divide your data sets. So we do small pre-processing. There is still some processing that has to be done with TFMs, but less than you would have to do with other methods. You don't have to spend hours finding the perfect pre-processing for your data. For TFM, it won't change drastically the performances of the models in the end.
Yeah. It's a bit obscure like that, but we have found, and I think a lot of people have found that using TFMs, you can rank how much they depend on the preprocessing that you apply. For example, we know that for MLPs, there are certain numerical encodings that work better than others. You know, RTDL or yeah, this one. For trees, there's been also some preprocessing work done, and we saw that for TFMs, when you vary the preprocessing that you apply to the different modalities in your table, it doesn't seem to impact much the prediction, the value of the prediction. So that's something that we don't know very much why, but yeah, they are less sensible to preprocessing.
Yeah, it comes mostly from the fact that this huge corpora of synthetic dataset that you generate will show a lot of variation. So essentially, he has seen all the different preprocessing possible during the pre-training, so he's less sensible to exactly how you're going to encode this column or another one.
Yeah, maybe. Yeah.
So one more question related to that. Do you need to still place some emphasis on pre-processing the data? For instance, maybe the data has a lot of columns in there.
You still have to do feature engineering.
You still need to do that.
Yeah, you still need to do feature engineering. You have prior knowledge on your data, so you know that maybe you have to create a combination of this column with these other ones, because you're creating signal. You're inputting more information in your datasets. And it works with TFMs, but you will gain performances if you know how to create information.
Okay, thank you.
Yeah. Yeah, it's still a classic model, but like it's less sensible to the type of scaling you use or the type of encoding you use for categorical columns, for example. Yeah.
So you said that you can really only work with maybe up to a few thousand rows.
Oh.
If you had a larger data set and you were to fit on a sample of that data set and then sort of try and predict progressively on chunks of the remainder of the data set, how well does that work?
So if I understand you clearly, what you're saying is that you want to chunk your test predictions to do them one by one, right?
Well, chunk by chunk. So,
Yeah.
so let's say you've got a 10 million row data set and you create 10,000 row chunks so that you can fit it into this.
Well, if you chunk the context, so the training, well, it would depend if your small chunk represents the distribution of the whole data set.
Yeah.
So you would have to find smaller representation by sampling rows that represent the difficulty of the task and the operation, the inductive biases that the model has to understand on your data to do the prediction on the test sets.
Yeah, as of now, they kind of have the same learning curve bias than classical models. So the more data you put in, the better it is as context. Sometimes there is too much noise in the data and more data is detrimental, but most of the time it's better. And yeah, the only thing that I think you mentioned is test rows don't attend to each other's in the mechanism, the attention mechanism.
Yeah.
So you can chunk your test rows however you like. You can do it one row per one row.
Yeah.
There is no attention between test rows.
So my strategy could work, assuming I can create a 10,000 row chunk that is representative of the whole data set in order to do the fitting, the fit step.
Yeah.
Yeah.
Yeah. But you can put more than 10,000 rows.
All right.
Yeah,
How many rows are in the
Well, with our current API, you can push 1 million rows. And we're going to deploy a new one next week, I guess, where you can go up to 4 or 5 million rows.
And in terms of the recent models, is that, are you doing, or is that something that your models do, or is that something other models can do?
Yeah, no.
It's something our models do, and
No, it's something like
the other one, API, don't do that.
But yeah, there is a push in the industry to go further and further and further. Everyone is pushing to the same. We want to put as much data as we can. But yeah.
So So in the previous cell, we just did a prediction using classic logistic regression. And as you can see, for TFMs, well, I do the exact same thing. So I do a fit. And again, the fit here is just concatenating the training data onto the test data and then pushing it to the server or pushing it into the models once you do the predict. So again, we don't fit on the data. It's just to mimic the same templates as classic scikit-learn methods. We have a fit and predict, but all the work is done in the predict method, where you push all the data at once in the model, or you push it onto our API, which on our side we push in the model. So we have fairly comparable results. Logistic regression works fairly great on these data sets. But don't look at the accuracy because it's a very unbalanced data set, so it's quite a lie. So if we were to compare both models directly, we see that in terms of WCAG, we are quite similar. Here we used a small version of our models. So one thing that we did not talk about is that TFMs comes with one hyperparameter, that is the number of shuffling of the features of your datasets that it's going to do. They are agnostic of the orders of the rows, but TFMs nowadays, and it's going to change in the future, are not agnostic to the order of the features. There is still, like in your LLMs, when you anchor positions from one token to another, saying this one is before, this one is after. There is the same in TFMs with regard to the features. Like in the training, the transformers has some positional encoding stating that this feature is before and this one is after. Therefore, if you change the order of your features, the prediction is going to change. So TFMs come with one mechanism where they do multiple forward paths in the models, and for each path, they shuffle the order of the features in order to try to recover the equivariance of the order. So here we used a small version of our model. And as you can see, the predictions are well calibrated. So we span the whole range of probabilities, and there are samples on which it's fairly sure and others where he has some doubt. Is it working for everyone on your computer? Is there any problem? Oh, it's okay. So, yeah, it's not wow effect. It works exactly as you used to work with your decision trees. You don't have to change anything. The only thing is that I don't have to find hyperparameters, and this will shine if we go on with other models. So in this first notebook, we just did plain predictions, but we did not try to really see how to check that the prediction models are accurate and to which extent it changed with regards of the sampling of the data that I do. What is my train set and my test set? So I guess you all know about this, but we're going to show a different problem that you could face if you're not careful about preprocessing. So in this first example, I just did some random preprocessing, but with one column that has access to the test. So the prediction is easy. And this is the most telling thing. So how many of you is working with this kind of prediction every day, like doing prediction on table data or having to be careful that the predictions are accurate and it's not just some artifacts of the selection of the train set?
Thank you, everyone.
So there is a lot of benchmarks out there trying to compare tabular foundation models against trees, and sometimes this is not really well done. So as you can see here, just by changing the seed, so by changing the random state, that is telling me I take these samples as the train samples, and those are the test samples. There is a lot of variation on the accuracy, so the quality of the predictions. I can also watch at the wrong metrics if I look at accuracy when I have some very imbalanced problem. Well, just a random predictor is going to have a very great accuracy, but it's just random. And if I want to compare models, I would want to see for multiple seeds, for multiple folds, if their confidence interval overlapped or not. So we're going to run a small benchmark using TFMs. And we're going to run it on 3 different datasets with 3 different models, random forests, XGBoost, and TFM. So XGBoost, you would have to find the good hyperparameters. I did not try to find them, so maybe you can play around in the notebook and try to find good hyperparameters to improve the performances. What's great with TFM is you don't have to. It just works as is. You don't have to find how many trees I want to put, the depth of the trees, and other hyperparameters.
Yeah, I think what's pretty cool is if you look at the benchmarks that exist out there, TFMs are a bit better than tree models, but it's when you tune your tree models, and it can take a lot of time, and sometimes in production it's not tractable. And so when you use default tree models, like with default parameters, in fact, TFMs out of box are way, way, way better than those models. And so that is a cool thing with TFMs, is that you can just do an inference, and they are optimized for every shape of data, every kind of data. They have been trained on a lot of different data, so you don't need to do hyperparameter search. That's really cool and really convenient for most parts.
Yeah, it helps to iterate faster on your.
Exactly.
We were talking about feature engineering.
Yeah.
You can do your feature engineering and test it right away. Don't have to find the good hyperparameters to experiment with your new transformation on your data. It's going to work just as before. It's the same model. You don't change anything about the model.
Yeah, say you work with a time series and you want to try to use different windows, different preprocessings. You can try it out directly with the models. You don't need to find the right one, the right hyperparameters, and it's really cool to be able to work on the other things around and not the model. So that's something that is enabled by those models.
So if we were to compare performances of the model, so we see that TFM shines on small data. So heart and shoppers are very small compared to adults, which is a dataset with 40,000 rows. So here we use a small version of the model. So here's having a hard time on this kind of dataset size. But if you were to use the larger version, it would be better than trees. And on these ones, I tuned the parameters to find the good parameters for the trees. So the only problem that we have with the prior plot is that we compared without distinction between the problem we're trying to solve. Like if I compare different folds, but I compare them all together, I'm not comparing for each model the same problem. So we're going to just look at the deltas of performance between the same folds, between the different models. So the idea is to see really is there a gain or not for the different models. So we see that there is a real gap for the small data sets, and for the larger one, XGBoost has a real gap on the small version of TFMs. Yeah.
Just wondering if you're familiar with a package called AutoGluon, which does AutoML.
Yeah.
Because I remember a while back managing to boost, get quite a significant boost in performance over XGBoost using that, and I'm wondering how well it would, the tabular models would compare with with that approach. But I think there's creates some sort of ensemble model.
Yeah, exactly. We are very aware of AutoGluon, and I think it's included in every benchmark nowadays.
Yeah.
And it's still like the TFMs are still better than AutoGluon.
Okay.
So I think in Tabular, which is the German benchmark that we were talking about earlier, they have like extreme versions of AutoGluon where you can let it run on 4 or 5 hours on your specific dataset, And yeah, I think I remember that TFMs are still better than this in one inference, so it's kind of cool.
I managed to, I was running it for like 15 minutes and getting pretty big.
Yeah. Oh, yeah, it's very...
just plain XGBoost.
It's a very cool package, yeah.
So running 4 or 5 hours.
4 or 5 hours. It's the extreme mode, and you can even use TFMs as a group in your ensemble with AutoGlean.
Of course, yeah.
So yeah, it's pretty cool. Yeah.
Yeah, you can, and there are some studies in research trying to understand are those embeddings good to represent the datasets themselves. Like you can try to do a pooling on all the embeddings because you recover all the rows embeddings. So you can do a pooling of all the rows embeddings. It gives you one embedding, and is this representation any good to map all your data sets? Okay, this one is very similar to this one is very similar to this one. So there have been a few papers in the last 6 months working on this. So different approach, use the model embeddings or try to create an embeddings based on meta features, statistical information that you would extract from your data sets. So yeah, it's...
Yeah, exactly. So yeah, I think that there's been a report on Kaggle-like competitions where they said that one of the new trends that emerge is to actually do that, use the TFM, take the embeddings, and put it in an ensemble of models or whatever, something that's better than the decoder, because the decoder that is pre-trained on this TFM is a simple MLP. So yeah, you can do much better with this representation, and you can extract the embeddings and put it in an ensemble of models or whatever, something that works.
So just for fun, maybe you can try on your own to change the size of the model. So just go to the cell where we set the TFM right here, and we can just put model equals Seldon, which is the name of our model. By default, it's a small version, but we can try with the large one, which is going to be a bit just not as fast as the small one. Yeah.
I've somehow managed to use up all my credits, and so I can't work anymore.
So on the
So
slide,
it's telling me I've only got 6 credits left.
Did you push the voucher I talked about in the presentation? Not.
Oh, yeah. Right. So
this one there.
Yeah. So I started with 53 credits, but I don't. Okay, I'll try putting that in and see if that's. Okay.
That's way more.
Yeah. I thought the QR code was doing that automatically.
No. We try to make it as simple as possible to use, but there are still something that. So we're just going to see the difference in performances, see what we can recover. And this time we with Random Forest, and we reduce the gap with XGBoost on the very large data set, which is one that we know where TFMs are not the best. So try not to cheat here and sell the TFMs are the best all the time. It's a fairly emergent field, so there'll be only 2 or 3 years of research, and not a lot of people are working on this kind of model, this type of models. So
Okay.
Well, we love working on it because everything is to be discovered yet. So,
but to be fair, I think the win rate on classical benchmark is about 90% for TFMs. So, but yeah, we just wanted to show that there are still datasets that we struggle on for some reason, and it's really hard to understand why. And at the same time, there are some datasets where we are really, really, really good against classical models. We have some clues about why, but.
So then again, the only difference is going to be, well, there's a lot of work, lots of effort that is put on making these models faster. Here on this kind of small data sets, there's the run, the trip to upload the data that's going to cost a lot, but we're trying to reduce this amount of prediction time in order to be as competitive as gradient boosting methods. But again, it's not the same type of models, so the flops required to run these models is way bigger. So you actually need a GPU. You can run locally for CPUs, but only for small tasks. So yeah, it's going to be a bit slower.
Sorry, yeah.
When the whole world is moving to like inference time, you're going to be competing to serve these models.
Yeah, we are. I mean, you can still distillate your model, but yeah, that's also one thing that we are pushing towards is making this inference time shorter and shorter and shorter. But again, at the same time, you have to compare it with the fit. In a lot of production environments, you have to compare it to the fit and predict time of classical models, yeah. Because your context changes all the time, so yeah.
I was reflecting whether, given that this was particularly useful for small data sets, right, where obviously things like trees struggle more, whether that being like good benchmark Bayesian models as well, where you use a kind of similar prior knowledge approach, right?
On really small datasets? You're saying that we should be really good on a really small dataset?
Yeah, I thought it would be interesting in comparison.
Yeah, obviously.
Bayesian models as well.
Okay.
You know, it's a good alternative when you have little data, similar.
Yeah, that's an interesting point, yeah. I know that PFNs are really good on small datasets, as you said. I don't know how they compare to classic Bayesian models. Actually.
You inject some prior knowledge.
Yeah, totally. Kind of the same thing, yeah. Yeah, you're right.
Yeah.
So I noticed from your table earlier that the models tend to be like a few tens of millions of parameters at the moment, which suggests to me that you could run them locally. So do people do that? Because obviously, I mean, obviously in terms of large language models, for example, you've got all these token costs, and you try and keep those minimal. But if you can run locally, you can, you don't have to pay these costs.
You can, but I don't know if people do it. I don't, because I don't want to wait. But yeah, you can do it for very small tables. You can run it locally on your CPU. If you have a GPU, it's even better. But even though there is not a lot of parameters, the fact that the data is very, very large, it's like if you had an LLM, a small one, but your sequence length that you would put inside your model is a million token or more. So it's going to be expensive and require a lot of compute power.
So, because you did say that it's that predict time that you pay the cost of using a large context.
Yeah, the unit, the token, the unit of cell is one cell. So if you have a context of 100,000 or a million of training rows, it's equivalent to have a really, really, really big context in the LLM.
But then there are mechanisms like you can integrate some mechanisms like KV caching in order not to reuse when you do your first forward pass on your training context. You can store much of the information, and a lot of compute can be removed for your test predictions.
Yeah.
Yeah.
Following up on the parameter, do you observe like scaling law applicable to this kind of foundational model? Because in LLM, like usually it's like bigger is better, more data, more parameters. Does it apply to like tabular foundation?
So on this question, I can cite you one paper, and there haven't been any so far that have done a larger work on that. It was a paper published 2 years ago by a Canadian team where they experiment a little bit with scaling laws, and what they show is that there are none when you train on syntactic data. Like at some point, you won't find any more information during training with a larger model. It's saturated very fast on the data you generate, but they showed that you may recover scaling laws when training on real data. So there's still a gap between real data and synthetic data, but they are not. We're working on it, and we will publish something in the coming month about this. But there haven't been a large work on trying to figure out what's happening with regard to scaling laws, because you have the size of the model, but also the size of the data you train it on.
Exactly.
Because you tend to train these models on fixed table size, which are fairly small, few thousand of samples, and you train on this. But you can also train on 2, 3, 4, 5,000 rows. So how does it vary the precision of the model on the downstream task? Those are scaling those stats. Haven't been published yet.
Yeah, I think the intuition is that you want to scale the architecture, the synthetic data generation process, and it's a bit of a hard thing to do to generate way bigger and way more data that is way more interesting. You tend to not scale that much the interestingness of your data when you scale it to way bigger or way more tables. So that's kind of a limitation, but we are currently trying to solve that limitation. So.
Right, last one. Could you go over your experience with time series data and foundation models?
Can we use time series with TFMs?
Yeah, we were talking together.
Yeah.
TabPFN.
TabPFN did it. A year ago, they experimented with trying to do prediction with time series, so they added some lag and did prediction. It works if your data is regular, like you have clear patterns. It tends to work. Otherwise, it's not a time series model. So you won't be able to predict the price of an action tomorrow, an option tomorrow.
It's not even like an XGBoost is necessarily going to be better than
Yeah.
like an ARIMA or a linear regression model.
Yeah, on very hard time series tasks such as market prediction, it's going to be hard. But yeah, they showed that it was really out of the box, really good against time series model, time series foundation models trained exactly on time series, just by putting the time series information as features. Yeah. Yeah, it really worked well. Yeah, it was competitive, I think, with Chronos early versions. So yeah. I don't think there is a paper. We don't have a paper on that now.
I think there is one. Time series PFN. There is one somewhere.
Yeah, you should check out their repo too.
Is everything working? Is there any problem?
Did you use the voucher?
No, unfortunately.
Like,
I have a QR code for that.
Yeah, ok.
Sorry.
Nico?
Zoom?
Tu peux remettre le voucher? Tu peux réafficher le voucher? Tac. Yeah, no, there is no QR code for the voucher. You have to type it.
Yeah, if you don't have credits anymore, just put this voucher and you will get 1,000
Yeah,
of
voucher.
them. So
Sorry.
1,000
have the same
credits
problem?
is like 1 million prediction rows that you can do.
I think it will be fine.
So it should be more than sufficient for today's session.
Yeah, okay.
That's all.
Yeah.
It's pretty cool.
You want us to up the mic, right?
Yeah, maybe a bit.
Okay. We'll try.
Thanks so much.
Is it good? We have to speak a bit louder. On the back.
C'est comment on zoome? Tu sais comment on zoome?
Tu fais pas, t'as pas un genre un commande option plus, un truc comme ça?
So on this notebook, we're just going to try to look at, there's a lot of ask around how the model does this prediction. So what are the features used to do this prediction? So we're just going to do a simple Shapley estimation to try to see if TFMs tend to take decision on the same features as tree-based models. So we're going to use again a small data set as the first notebook, the heart disease data set, and run a Shapley on the prediction of our model. So it's going to be a bit slower because it's a lot of round trip.
Should have an option to remove the print.
Là, ça va être la queue. Je pense qu'il y a du monde qui tape dessus.
Ouais.
Tu vas leur demander d'utiliser le smart peut-être.
Do you think it's feasible to apply conditional models in case when training data is scarce, say less than 10,000 points, but production would potentially have hundreds of thousands of data points? Do you think that's an area where models can shine? Or
Could you repeat that?
so I'm just
Where
imagining a scenario where the training data is scarce, we get small data, but in broad we have all the magnitude more data points.
So you're saying a few train and a lot of...
If I train on 10,000 points,
Yeah.
inference on 100,000 points, there's a scenario.
I mean, you're going to have the accuracy of a model trained on 10,000 points, so depends on what distribution you try in a model.
Okay.
I guess, I guess the more data you have, it's a bit of the same as for classical models. So the more training data you have, the better it gets. It doesn't really matter on the number of inference rows you have, as long as you can model the distribution, I guess. So, yeah.
So we can do Shapley values even for this kind of models. It's usually asked for with the companies we work with. They want to know how a model tends to do a prediction. We can see that these models are fairly agreeing on the first, on the biggest, most important features. Do you need interpretation in your daily jobs? Like if you run a model, do you have to prove why the model took this decision or not? Because with LLMs nowadays, we don't really try to understand why we have this prediction. so we don't care about it. But for tabular predictions, well, if you work on credit fraud or even medical data sets, you tend to want to know what happens and why I have this prediction. So classic statistic methods like Shapley value are working if you want to have some mathematical proof. But otherwise, there's a paper that's going to be published soon on that this kind of models allows you to also look at internally inside the models how it takes this decision, not purely based on statistics. If you were to look at attention mechanism, why do I take these decisions? Which training rows were the decisive information for the model to take a prediction for one test samples? What was it looking at in the training context to do, okay, this patient is going to have a heart disease. Is he going to look at, which patient is he going to look at? So you could have this kind of information since it's attention-based. Depends on the threshold you put on how much, how do I decide what is interpretable or not. It's going to be published soon.
Yeah, sorry. Yeah. It's sample shap. Sample shap, yeah. It's I think the main intuition is like TFMs are like a bit more than just retrieval models. So there is way more information in your model than just looking at the attention between rows and saying, okay, for this inference row, I looked at these train rows. Actually, you can do much more than that, and this is what we tried to do in this sample shap. Yeah.
It's really interesting to see that the standard model has some clustering around exactly zero shap values. But you see that the blue and the red, if you look at the first and most important picture, they are roughly the same, similar distributed across the two, but in the middle we get these zero clustering.
Yeah.
Is there anything theoretical that gives that explanation? Why?
Maybe some theory, like as we were stating earlier, so this is based on what decision you take with regard to the features, and the latest models, the latest TFMs tend to compress this dimension, so you compress the information of the features into one token. So based on probably these data sets, he has decided that the most important features were the one above. So he's taking more emphasis on these ones. And for the other one, well, it's not that they don't exist anymore, but he decided that to discard them somehow.
Yeah. Maybe I was ambiguous with my question. Yes, I think, but what we see that on the right side, the shap value takes 0 on yes, on that case, and they are clustered on that compared to the other one where we see a spread out. Usually, that feels something similar to me, like when a linear model pushes some of the coefficients towards 0. That's why I asked if there is any theoretical something that would push to see these kind of zeros for those predictions, for those rows when we have that actually there to be 0.
No, I don't have any ideas. Do you need this one?
No, sorry. I don't have an intuition in that.
So this question relates to the last one, but at a very high level, is there any intuition or I guess, any theory why, from a scaling point of view, even though the shape is almost the same, but of course there's some differences, but the sharp ratios or the sharp values are slightly different than in scale between the two?
I don't know. Really, I don't know. I'm not a sharp expert, so I don't know.
The question was on the scale of the sharp values. That is also very different from, and that's a good question actually.
I'm guessing that obviously the reason why you're also comparing it against an established model is that you're indicating that the TFM approach is...
Yeah, it's sound. The predictions are not random, so if you trust gradient boosting methods predictions, well, you tend to see that TFMs take their decision based on the same information, so it's not coming out of nowhere and it's not random prediction. or something that we won't understand why it does that.
All right, okay, thank you. So just to follow up on that, you're essentially using the XGBoost model, its behavior as revealed by the SHAP values to validate what you're seeing from the tabular foundation model.
Yeah, exactly. Yeah, if people work for 10 years with gradient boosting methods, so you trust them. You come up with a new technology that is transformer based. So usually you think about LLMs where you don't trust them. So you have to show some things to prove that it's not just random prediction, that the decision is sound. Yeah.
So you have to type, you have to type that, There is, I think there's a. No, sorry, the QR code doesn't work.
Doesn't work. Okay.
I think you have to type in credits. There is a voucher right here.
Thank you very much.
Sorry, no, it's not optimal. Yeah, so for everyone, the QR code is just for the 50 credits. If you want more credits, you need to go to the client and type this voucher. There is in the credits side, you have a type voucher and you can type this, and it should give you infinite credits basically, just for today. It's not gonna it's not gonna work for. Maybe.
Okay. Nice. Okay. Thank you.
What was the question?
So there was an interesting question with regard to the numbers of CLS. So classes you can push into these models. So there is no problem with the numbers of class. It was trained on limited numbers of class, but you can predict more. You can go up to 1,000 class for the predictions. And we did not present it today, but there is also a regression models on the API because TFMs can also do regression. So yeah, it's not only classification tasks.
Yeah, it was trained to, like Nicolas said, to a limited number of classes during pre-training. But with a hierarchical approach, you can scale this up to many classes. So, and it works quite well. Or you can use the representation directly to train another head, another decoder. Or you can use directly the representation to do a kind of retrieval based task on your many class problem. It also works. There are many ways to deal with a huge number of classes.
Are there any more questions about the notebooks or TFMs? Everything clear? Yeah.
So it's clear from these notebooks that the SHAP values, at least for this particular data set, the SHAP values for the cellular are, the magnitude is a lot smaller than the SHAP values for XGBoost. Is that something you find in general, or is that just specific to this? And
it's in general, yeah.
Sorry?
In general.
In general.
Yeah.
Do you have an explanation for that yet?
I don't.
Okay.
I have a colleague that works specifically on this kind of questions that would have loved to answer your questions, but I don't know.
But yeah,
it's just an interesting thing because they seem to be doing something very similar, and then you notice the magnitude.
Yeah.
Suddenly.
And you have kind of the same effect when you try to compute permutation importance or such importance scores.
Yeah.
I think the intuition is about feature interaction rather than univariate features information.
Yeah.
But yeah, I don't have a magic answer for that effect, yeah.
It might be an interesting paper in that, for all you know.
Yeah, we are working toward that paper.
Is there any questions about TFMs in general? Like, how is it they are trained and how it differs from trees? Because I know that I had a hard time to understand how it works at first. It's weird.
Any questions? Anybody?
If you wanted to fine tune.
Yeah, you can. You can fine tune these kind of models.
I mean, how would you start? So I guess you go to Hugging Face, you can get like a pre-trained one, is that correct? And then you can,
Yeah.
is that right?
Yeah, I mean, I think it's the same with the classic Angular models.
Okay.
So you can fine tune all the weight. You can. I don't think LoRa works as well here, from the experiences that we've done. I think the classical fine tuning is a bit better.
Fine tuning papers for TFMs tend to show that you have to fine tune all the weights. Then just there are, if you go into the TabICL repository, there are a recipe in how to fine tune TFMs on your particular tasks.
It's rather classical.
Yeah, it brings some performance, but sometimes it doesn't.
As for fine tuning, does it work with few shots as well, or you have to?
Yeah.
Does it work with few shots?
Yeah, it does. Okay, so again, there's been some study on that subject. How do you fine tune when you have only a few samples? And so something that tends to work a bit is to use tabular diffusion models to generate more samples and then fine tune on it. And surprisingly, it works quite well because you're kind of replicating the information that you have in your few samples to a bit more samples, and you can fine tune on it. So that works, yeah. Use classical CTGANs if you've heard of it, or the diffusion model CTGAN. I don't know if you. But you can create more samples from your synthetic samples from your real samples. That works.
Any advice on, I think that when you started with the theory, any advice on how you sort of, how you correct the distribution? Because you have like a distribution function for generating your synthetic data.
Yeah.
Is there any advice on how you go about that? You know, for instance, if you have your own, if you want to tune and then you want to sort of align that to your own domain?
I think something that kind of works and it's easy to do is trying to find symptoms of your specific data.
Yes.
That is different from usual generic data, academic data. So is your problem really imbalanced? Maybe you're gonna want to work on that. Are your distributions of a certain type? Maybe if you're working, for example, on financial data, you want to have student-like distributions for the target and the features. So yeah, it works quite well to trying to understand with classical EDA the kind of data that you have and pre-train on that data.
Okay, thank you.
But you have to respect a kind of diversity too. There is a trade-off. You want your model to learn on a diverse set of data sets.
Generalize.
Exactly. There is a generalization trade-off, yeah.
Thank you.
So for the last few minutes, maybe I can direct you to the benchmark we published a few days ago, where we compare all the large, the SOTA TFMs, so the best TFMs that you can find out there, against traditional machine learning algorithms. So You can compare with regard to the task that you want to solve. Is it healthcare, behavioral, or I don't know, finance, games, and so on. We've tried to put as much dataset as we could, but by being careful that it was not the same dataset twice.
Yeah, we curated the available public datasets to have a list of sound, reasonable, on various verticals, to let the user explore what kind of performance you can find with TFMs. And as we were talking about earlier, you can see that the win rate actually is actually really good with TFMs compared to classical baselines. And yeah, I've got to say that all these baselines have been tuned, ensembled, and such. And so the result is quite something.
Can you show this thing on computer vision?
On computer vision? Yeah, okay. Try the computer vision. Okay.
So far it's only classification.
Yeah.
So you cannot ask about what's going to happen for my regression problem, but in a few months there will also be the exact same thing for regression problems. So maybe the big question is, are you convinced about TFMs? Would you want to use them for your future tasks? Or do you need more convincing? Is there any questions about TFMs?
I think it's a step in the right direction. But I do think that, to the question that was asked earlier, I think it's important to understand the sharp analysis, just understand that scaling difference, and just trying to get into the nuts and bolts of that, because explainability, even more so for a, for a transformer or for a large language model, is really important. So
we know.
But I think it's a step in the right direction, because I think this is quite interesting. And then also the other thing is the challenge you described earlier about large data sets. I don't know how you, I mean, is that purely just a compute challenge? So a scaling challenge?
No, I don't think so.
No, it would be too easy. Put more compute and then it's okay. No, it's not only a compute problem, it's also that with this very large context, your attentions, also your probabilities that you have to find on your context are very diluted. So you have to find ways such that the model doesn't lose itself in the context and still predict something interesting. So it's not only a compute problem, it's also like a theoretical problem on how to tweak attentions, the way I look at my queries to do the prediction.
Yeah, the same way I think LLMs had to deal with learning better positional encodings for large context. We have, not on positional encodings, but we have kind of the same problems with TFMs, so it's being solved as we speak.
Just from a ballpark, I mean, what's the ballpark figure for the context length?
For the context length? I think TFMs shine versus classical XGBoost and deep learning methods on the few hundreds to thousands, because those classical baselines are not that good. But then you can scale up to, I think, 100,000 and have still an edge with TFMs. Maybe when we get to the tens of millions, the classical methods tend to outshine TFMs,
But it will depend on the problems you're going to solve. So you will find data sets on which we are better with 1 million rows, but on the other side, you can find a data set with a few thousand rows where gradient boosting methods are better.
It's moving fast. So 2 years ago, when TabICL was first introduced, the ballpark of performance was like 100 rows, something like that. And in 2 years, we scaled up the performance to thousands, 100,000 rows. So I think it's really.
And is it true that when you compare this to autoregressive models, i.e. what ChatGPT, I mean, there you can actually get away with a lot because you're only training the model based on a given prompt with some contextual information. So typically the 128,000 tokens, typically for GPT-5, it's enough 4.5 or whatever, that's kind of manageable. But here you have to give it the entire data. Is that correct?
Yeah.
So I think that's the difference. Yeah, is that right?
Yeah. Yeah, it's gonna, at one point, it's gonna be a problem that you still have to give all your training data. If you want to scale to 1 billion, maybe.
Okay.
We don't have enough GPUs for that. So we have to find a way to, that's, I think, one of the introductory subjects was about context. Like, how do you do how can you prompt the model with the good context? Because I'm pretty sure that you don't need a billion data for each point that you have. You need a billion data to understand the whole distribution, but maybe you don't need for each point. So I think that's a direction of research that might be really interesting to understand what context each point that you're trying to infer on needs.
Okay. Thank you. Yeah, makes sense.
But with the current tokenization, yeah, you need to put the whole table, the whole training samples. Also, there could be something about tokenization. There are a lot of things to try with those models.
Any thoughts on benchmarking prediction rates?
Yeah, every time we were like, yeah, we need to put the latency, but the problem is that if you want to, with the amount of hyperparameters such that you do for all the models, you run them on different machines. So to be fair, we didn't want to compare models that have not been run on the same CPUs or on the same GPUs. So because of the scale, here there is no information on latency. But yeah, TFMs are going to be slower than gradient boosting methods because it's run on GPUs.
If you don't need to tune it.
If you don't need to tune the XGBoost. So you have to take the whole pipeline in mind.
Yeah.
When you have your gradient boosting methods, you have to find the hyperparameters and so on. So this is going to take times, while TFM, you just have to put your data in and it's finished. So you might lose 10 seconds here, but you might win a few hours before.
Just following up on that, it seems to me, obviously, it's the time it takes you to train your model, and then there's your prediction latency. Unless I'm missing something, it seems to me the prediction latency is always going to be slower with the TFM. For a start, it's a big neural network rather than even XGBoost. You might have a few hundred trees.
Yeah.
That's not going to be anywhere near as
TFM.
computationally intensive as a big neural network.
Yeah. Yeah, exactly.
Yeah.
You can always fight to make it faster, but it's going to be probably engineering tricks rather than...
Yeah.
Or you have to change the model. You have to do something different.
Okay, thank you very much for attending this presentation.